Hi, good day. So let's have an example for the selection of a section for a compression member. Okay, so let's have this example. Select the lightest W14 available for the service column loads. So a dead load of 600 kilonewtons and a live load of 1000 kilonewtons. So we are to use Fy equal to 345 megapascal. So this is our column. Okay, the unsupported length for both axes. So that is for the y-axis and x-axis is equal to 4.5 meters. Okay, so first, so let's have our load combination. So load combination for the LR FD for this example. So let's say the ultimate load is equal to this is 1.2 of the dead load plus 1.6 of the live load. So we'll be having the ultimate load P sub U is now equal to 1.2 of that is 600 kilonewtons plus the 1.6 of 1000 kilonewtons. So we'll be having the value of P sub U is now equal to this is 1.2 of 600 plus the 1.6 of 1000. Okay, we have that as 2,320 kilonewtons. So this method is our first method how to select the lightest section for a compression member. So secondly, we have, or for the second step, so we are to assume the value of our slenderness ratio. That is the KL over R. So for this example, I'll be using an estimated value of the slenderness ratio 50. But conveniently, you can assume the value of KL over R from 40 to 60. So just for this example, I'll be using 50. So if we have now this assumed value of the slenderness ratio, we can now compute for the F sub E. So F sub E is equal to, that is the pi squared, or this is the Euler's formula. So pi squared E divided by the slenderness ratio squared. So let us compute for this value. So we have F sub E is equal to pi. So for steel, that is 200,000 megapascals. Then to be divided by our estimated slenderness ratio, that is 50. So this is 50 squared. So we'll be having the value of F sub E. This is ship pi squared multiplied by 200,000 to be divided by the estimated slenderness ratio 50 squared. So we have that as 789.568 megapascals. So we have F sub E is equal to 789. So 789.568 megapascals. So if you now have F sub E, okay, how do we compute for the F sub CR? So if you have to recall, from our previous videos, so we need to consider these two conditions for the computation of the F sub CR. So the first condition is if the slenderness factor or slenderness ratio, KL over R, is less than or equal to 4.71 of the square root of E divided by Fy. Okay, so that is our first condition. We have A, if the slenderness ratio is less than less than or equal to 4.71 of the square root of the modulus of elasticity divided by the Fy. So we have our KL over R is equal to 50. Is it less than or equal to 4.71? The square root of 200,000 megapascals divided by our Fy is 345. So this is 50 less than or equal to that is 4.71, the square root of 200,000 megapascals divided by 345 megapascals. So that's 113.403. So 113.403. Since it is less than our slenderness ratio is less than this value on the right, we can now compute for our f sub CR. So f sub CR for that case is equal to, you have 0.658 raised to Fy divided by f sub E, then multiplied by the value of f sub Y. So we are now ready to substitute. We have the f sub CR is now equal to, this is 0.658 raised to f sub Y 345 divided by the computed value of f sub E 789.568. And then multiplied by 345 megapascals. So our f sub CR is now equal to, we have 0.658 raised to 345 divided by the computed f sub E, that is 789.568, then to be multiplied by 345 megapascals. That's 287.338 megapascals. So 287.338 MPa. Okay, so we have now this f sub CR. We can now compute for the capacity, or yes, the required area of this given stress. So basically, how do we compute for P sub U? That is equal to P of P sub N, or equal to the P multiplied by f sub CR, then multiplied by the required area. So basically, the required area is equal to the P sub U divided by P of f sub CR. So what is our ultimate load? The ultimate load is equal to 2,320 kilonewtons. So we convert that one to newtons. So our P sub U is 2,320 kilonewtons, then multiplying 1,000 newtons. Then divided by P, so for LRFD, our reduction factor is 0.90. Then F sub CR, the F sub CR is equal to 287.338 megapascals, or basically the newtons per square mm. Since we are looking for the area, so obviously the unit will be in square millimeters. So this will be the required area based on our ultimate load. So computing for that value, this is 2,320, the ultimate load, times 1,000 to be in newtons. Then divided by 0.90, multiplied by 287.338 megapascals. So the required area is 8,971.239. So 8,971.239 square millimeters. So this is the required area based on our initial computation. So we may proceed to our database. What section will have a greater area, or what section will be having what section do we have with this area 8971 or greater? So let's have our database. So again, we are looking for W14. So we can press Ctrl F, then W14. Then just press Enter. So these are the section of W14. So my table is in square inches. So let's have the lightest. So let's try W14 by 48 with an area of 14.1. Okay, so class, let's try W14 by 48. So its area is equal to ay 14.1. So this is 14.1 square inches multiplied by 25.4 squared. Okay, for our answer to be in square millimeters. So do we have a value greater than or equal to this required area? So this is 14.1 multiplied by 25.4 squared. That's 9,096.756. 9,096.756 square millimeters. Again, we are looking for a section with an area equal to this value or greater. So since this is greater than 8,971 and it is a close value to this one. So let us try this section. And then one thing more, when it comes to wide flange, so the moment of inertia with respect to the y-axis is always less than the moment of inertia with respect to the x-axis. So our critical radius of gyration is always the ry, or with respect to y. So let's have its the radius of gyration with respect to y for this section. It is 1.91 inches. So it is 1.91 inches multiplied by 25.4. We are multiplying 25.4 millimeters. So this is equal to 1.91 inches multiplied by 25.4. So it's 48.514. So this is 48.514 millimeters. So let us check this section if it is adequate. Alright, so let's have its actual slenderness ratio. That is the KL over R. Again, we are considering with respect to the y-axis since it's more critical compared to the x-axis. So what is our what is the value of our effective length factor? So it is fixed at the base. Okay, so considering the y-axis, fixed at the base and hinged at the top end. So we are using the recommended values. So hinged at the top end and fixed at the base, we are using 0.8 for the effective length factor. And the length of our member is equal to 4.5 meters. So this is we have 0.8 multiplied by 4.5 meters or 4,500 millimeters divided by our ry. This is 48.514 millimeters. So let us have its value. 0.8 of 4,500 then divided by 48.514. That is 74.205. 74.205, that's our slenderness ratio. Then for the computation of our f sub e, that is equal to pi squared times e divided by the slenderness ratio, quantity squared. So this is equal to the pi squared, 200,000 megapascals. We are just repeating our previous procedure. So that is pi squared times 200,000 megapascals, then divided by 74.205. And this is equal to, this should be squared. And that is equal to, so this is shape pi squared multiplied by 200,000, then divided by, we have 74.205 squared. Okay, that is 358.479. So 358.479 megapascals. So by the way, our slenderness ratio is less than 113.403. So that's our first condition a while ago. So how to compute for the f sub CR? Since we have the same values of Fy and E. So we are just using a new value or the actual value of the slenderness ratio of the chosen section, okay, the W14 by 48. So for the value of the f sub CR, that is equal to, we have 0.658. Okay, then and this is raised to the value of f sub y divided by f sub e, then multiplied by the f sub y. So this is now equal to 0.658 raised to f sub y 345 divided by 358.479. And then to be multiplied by the value of our f sub y, 345 megapascals. So let's have the value of f sub CR. We have 0.658 raised to 345 divided by 358.479. Then to be multiplied by 345. That is 230.611 megapascals. So 230.611 MPa. So let us check the capacity of this section. That is the P sub U is now equal to P multiplied by F sub CR, then multiplied by the area. So again, our reduction factor, factor for LRFD is 0.90. Our F sub CR is 230.611. Then we have the area, that is 9,096.756. And the resulting unit for this one is in newtons. So to be multiplied by 1 kilonewton is to 1,000 newtons. So we will be having the P sub U is now equal to, that is 0.9 of 230.611. Then we have the area, that is 9,000. Area of W14 by 48, 9,096.756. Then to be divided by 1,000. Okay, so this is unfortunate since 1,888.031 kilonewtons. Okay, this is the capacity of our trial section, the W14 by 48. But our ultimate load, the actual ultimate load or the required ultimate load is 2,320 kilonewtons. So that makes our trial section W14 by 48 is not adequate. Okay, so our trial section is not adequate. So which means we need a bigger section. So we go back to our database, then try a larger section, larger than W14 by 48. Okay, so let's try a bigger section. Okay, so let's say I'll be trying. So I'll be trying W14 by 61. So for the properties of the W14 by 61, so we need its area. So the area is equal to 17.9. So let's try W14 by 61. So its area is equal to 17.9 square inches. So this is to be multiplied by 25.4 squared. So the area of this section is now equal to Right, so this is 17.9, then multiplied by 25.4 squared. That is 11,548.364. So 11,548.364 square millimeters. So again, when it comes to the radius of gyration, if we are to observe again the moment of inertia with respect to x and y, so our moment of inertia with respect to the x-axis is 640, and with respect to y is only 107. And our radius for gyration with respect to the x-axis is 5.98, and so our ry is 2.45. So again, so we have the moment of inertia with respect to the x-axis or with respect to the y-axis is less than the moment of inertia with respect to the x-axis. So our critical radius of gyration, we are considering our ry. So the value of ry is equal to 2.45. So this is equal to 2.45 inches, to be multiplied by 25.4. So our ry will be equal to 25.4. So we have that as 62.23 millimeters. 62.23 millimeters. So these are the properties of our new trial section, the W14 by 61. So we are just to repeat the process, okay? Same as this trial section, the W14 by 48. So let's have our slenderness ratio. So for the slenderness ratio, this is KL. The KL divided by R. So again, with respect to the y-axis. So we have the same effective length factor, that is 0.8. So the length of the column is also 4,500. So we have a new radius of gyration this time. This is 62.23. And this is now equal to 0.8 of 4,500 divided by 62.23. That is equal to 57.85. And again, this is less than the 113.403, or that is the same as the 4.71, the square root of E divided by Fy a while ago. So we have that value as 113.403. So let's have the value of the f sub E. That is equal to the pi squared multiplied by 200, or that is pi squared multiplied by E divided by the slenderness ratio. So KL over I with respect to the y-axis. So we are now to substitute. This is pi squared multiplied by 200,000 megapascals divided by our new slenderness ratio, the 57.85. And this is now equal to, this should be squared. Okay, we have shift pi squared, then multiplied by 200,000, then divided by 57.85, then squared. It's 589.825. So 589.825 megapascals. So for the value of the f sub CR, this is equal to 0.658 raised to the value of f sub y divided by f sub E, then to be multiplied by the f sub y. Okay, so we are now to substitute. Okay, we have 0.658 raised to Fy 345 divided by f sub E, the new one, 589. Okay, that's 589.825. Okay, then to be multiplied by 345 megapascals. So we have the value of the f sub CR is now equal to, we have 0.658 raised to Fy. That is 345 divided by 589.825. Then to be multiplied by 345 megapascals. So 270.082. So 270.082 megapascals. So we have now the f sub CR. Let us compute for its capacity. So the P sub U is equal to the reduction factor of P multiplied by the f sub CR, then the area of our new trial section. So the area of this trial section is 11,548.364. So we have now this value of P sub U. Reduction factor is 0.90. F sub CR is 270.082 megapascals. Our area is equal to 11,548.364. Again, the unit of this value or the resulting value will be in terms of newtons. So multiplied by 1 kilonewton is to 1,000 newtons. So we have the value of the P sub U is now equal to 0.9 of F sub CR, 270.082. Then to be multiplied by the area of this section, 11,548.364. So the resulting value is in kilonewtons or newtons divided by 1,000 to be in kilonewtons. So this is 2,807.105 kilonewtons. So again, what is the required PU for this example? Or that is what is the actual ultimate load? 2,320. And the capacity of our new trial section, the W 14 by 61 is equal to 2,807.105, which is greater than the P sub U or the actual P sub U of 2,320 kilonewtons. So we can now conclude that the W14 by 61 is adequate. So W14 by 61 is adequate to carry the P sub U 2,320 kilonewtons. So we may use this section. But if we are to go back on our database, I skipped this W. I skipped the W 14 by 53. So I just want to make sure that our new trial section will be adequate. Since if you are to observe, the radius gyration of the W14 by 48 and W14 by 53 are very close. Okay? 1.91, then 1.92. Maybe we are not to arrive with a great change when it comes to the capacity since the radius of gyration are almost equal. Then when it comes to the areas, the area of the W48 is 14.1 and the area of the W14 by 53 is 15.6. Again, these are close values. So I just wanted to make sure that our new trial section, the W14 by 61, will be adequate. But you can check, okay? Why not try on your own? So just to be more, let's say, if we can have the more economical section, okay, try on your own. Try the W14 by 53. Okay, so, but this is our solution and that is our procedure. Okay, this is our method 1. How to select a section, okay, in designing a compression member.